In this video, we're going to talk about how to remove things from the heap. Now, since we have a min heap, we'll be removing the smallest element from the heap. But even if this was a max heap, the concepts are the same. It's just that we're doing a different comparison. And no matter what kind of heap we're removing from, we're always only going to remove the root element. However, since heaps have a structural constraint, they have to be complete. That means that we'll actually be removing a leaf node, and we'll discuss how that works. So here's our removeMin method, and the simplest case is if the heap is empty, it's very easy. We throw in empty collection exception. If the heap has one element, we'll pull the element out of the root, and then we will set everything to null inside the heap because there are no more elements that exist inside the heap, and we'll return the element. Now, the more interesting case is what if there are elements in the heap? Now, in this case, we're still going to pull out the min element because we're going to need to return that. And then, since the size is not 1, we're going to go into this else case. So in this else case, we're going to do 3 things. We're going to find the new last node because we're going to actually delete this node. Even though we're removing this element, we delete this node. Then we're going to set last node to be the new last node that we found, and we'll talk about how that function works in a moment. Next, we're going to copy the element from the node we're deleting to the root. And then finally, we're going to shift it down until we have a proper heap order. So let's walk through this. The first thing is we're going to find the new last node, and we're going to call that new last. So that would be this node. Notice it's to the left of our original last node, and we're going to set the new last reference equal to that node. Now here, this node is not the left child of its parent. That's what this checks. Last node get parent get left gets the left of last node's parent, and then this checks to see is it the same node. It's not in this case, so we go to the else case and we set the parent's right to be null. So that erases this link. Not to worry, we still have the last node reference because we haven't pulled that element out yet, which is what we do here. So now we set the roots element to be 8, and now we can safely update the last node reference to be the new last node. And so this node will get garbage collected. We have a problem because 8 is larger than 5 and 3, and that violates the heap ordering constraint. So we're going to call heapifyRemove, which is another function we'll discuss in a moment. And that's going to compare 8 and 3, realize there's a problem, and is going to move the 8 down. Then it'll compare the 8 and the 9. It's always going to compare with the smaller child. And here, 9 is smaller than 11, so we compare with that. 8 is smaller than 9, so it's smaller than both, because if it's smaller than the smallest child, it's smaller than both children. So therefore, it's properly ordered. So we're done with heapifyRemove. And then we're going to return min element, the element that was originally stored at the root. Notice we have a new root, we have a new last node. Now notice we have the same root, but it holds a different element, and we have a new last node. Okay, so let's see how getLastNode works. So we're going to see 2 examples of this working just so that we can see how all of this code works. So the first thing we're going to do is create a reference called new last node that refers to the original last node from the heap. Then, as long as that's not the root, and as long as it's the left child of its parent, again, new last node, get parent, get left, that gets the left child of new last node, and we check to see, is that last node? This is a right child, so that's going to fail, and so we'll skip this for now. Then, if we're not at the root, because the root creates some different things that we have to be aware of, if we're not at the root, then we're going to go to the left child of the parent. Here we're the right child, but since we're not at the root, we're going to go to the left child. Now, once we've done this, we need to go to the right as far as we can, but there's no right child here, so we're done, and we can return the new last node. Now, let's say we want to remove another node. So now notice this node has been removed. Now the last node is 20. If we're going to find the new last node here, notice it's not quite as simple. Before we just went to the right child of the parent. Now we've got to go back up to this branch, then go to the left, and then down to the right as far as we can. And the code will do that. So we start off, we set our new last node equal to the original last node. Now notice this case does succeed because we are the left child of the parent. So we're going to set new last node equal to the parent. Now here we're the right child, so we can exit out the loop. And if we're not the root, now we're going to switch, just as we did before, to the left child of the parent. And then this last loop will go as far to the right as possible. And so here, the right child of this node is not null, so we will go to the right. And then here, there is no right child, so it's null. So we can return the new last node, which will be this node right here. I would recommend that you try to draw some heaps and trace through this code. Just make sure that you draw valid heaps, because if you don't have a complete tree, this is not going to work the way you would expect. But it's definitely good practice to try to work through this on your own with a pen and paper, just so that you can get a better grasp of how this works in different scenarios. So the heapifyRemove is the method that makes sure that the ordering is correct. So if you'll remember in our removeMin example, we put an 8 up here at the root, which is bad. So let's see how heapifyRemove works. So the first thing we do is we set a reference called node to the root, and then left and right references to the root's left and right children. And we'll create a next reference that we'll use to help us navigate through the heap. So there's 3 possible cases for any node. There may be no children, in which case both references are null. That's not the case here though. But if that's the case, we set next to null. Then else, if the right is null, that means that there is a left child. So we set next to left. And you may wonder, how do we know there's a left child? Well, this first case checks to see, are they both null? And if left was null, left would be null and right would be null. But we know that's not the case. So now if right is null, then we know that left isn't null. So that's how that works. Again, though, that's not the case here. So we know there's 2 children. And what we're going to do is we're going to compare the elements at left and right. And we're going to choose the smallest. So in our case, 3 is smaller than 5. So we set next equal to the right node. So now let's move down through the method. And the first thing we're going to do is we're going to store the element stored at node. Now remember, that's the root right now. So that's the element that was in the last node of the heap, but we removed that node, and so we moved its element to the root because that's where the min element was stored that we're removing. Again, it's a little confusing. Just remember we're working with heaps, so we have to maintain that structure. Remember in removeMin, we took the element out of the root, we replaced it with the element that was in last node, and now we need to fix the order. So 8 is safely tucked away in our temp variable. And so now we're going to do this loop. Now you'll notice this loop looks an awful lot like what we saw at the start of heapifyRemove. And in fact, the logic is identical, except that now we're navigating through the heap as opposed to starting at the root. We can see that next, which is the smallest element stored in a child of node, is less than the temp element, meaning it's in the wrong order. So we're going to set the element of node to the element of next. So now we have a 3 in node. And again, don't worry, we haven't lost 8. It's still in our temp variable. Then we're going to set node equal to next. We're going to set left and right to the left and right children of node. And then we're going to look for the smallest child. Same logic as we had before. If both are null, that means there's no child, so we set next to null. Otherwise, if that's not the case, we check to see, is there just a left child? If so, we set it to that. And then if we get to this case, that means there's 2 children. Let's find the smallest one by comparing the element at left to the element of right. And in this case, the element to the right is smaller, so we set next to that. Now here, notice that the element at next is greater than the element in temp. And so that means we're done looking for smaller elements because this was the smaller element stored in these 2 nodes. And this element is smaller than the temp value, meaning that the temp value is smaller than both of these, meaning we're going to put that into the element that node is pointing to. And that completes our heapify. And now we have a nice heap that has the correct ordering.